This is section 8.3, trigonometric integrals. In this section, we're going to study a particular type of integral that has powers of sine and cosine within the integrand, or powers of secant and tangent, where one of those powers has to be a positive integer. And so what we try to do with this is try to recreate a situation where we have the ability to use the power rule. For example, this one, which is something that you could do before today even. If you had, for example, sine to the fifth of x times cosine of x dx, well, if you let u be the inside function of raising something to the fifth, du is cosine x dx, which of course is exactly what we need and exactly what we have. So that part is du. And so this becomes u to the fifth du, which is 1/6 u to the sixth plus c. Going back to the original variable, that's 1/6 sine to the sixth of x plus c. So that's kind of the basic idea behind what we're going to be trying to do. But the ones that we're going to be given to look at in this section are a little bit more complicated than this one. This is one that you could have done before today using u substitution techniques. So what you need to be aware of for this one where you have a power of sine, say they use m, of x times the power of cosine of x dx. There are a few things that you need to remember about sines and cosines and being able to write one in terms of the other, which is a big part of what this involves. And there are certain trig identities that you're going to need to recall to do this type of problem. So we need some identities that relate sine to cosine. Well, the ones that come to mind to me are the Pythagorean identity, sine squared x plus cosine squared x equals 1. And you could either, in this section, you'll either be solving this for sine squared x, getting 1 minus cosine squared x as a replacement for sine squared x, or solve for cosine squared x, getting 1 minus sine squared x, and use 1 minus sine squared x as a replacement for cosine squared x. Another pair of identities that come to mind are the half-angle identities, or I guess more accurately, most people call this the power-reducing formulas. So if you have a sine squared and you want to reduce its power, you end up getting 1 minus cosine to the first of 2x all over 2. And the power-reducing formula for cosine, to go from cosine squared, that is 1 plus cosine of 2x, double the original angle, over 2. And so those are the identities that we will be employing in order to get something that looks like the integral to the left, so that we can use the power rule. That's kind of the big idea here. So let's work through an example, and then we'll see, kind of how we can maybe slide into what the book has as a sort of a laundry list of things to do and things to look for. If we're going to be doing this process and using the power rule, like the one we did above, eventually we'll want it to look a lot like that, and either u will be sine of x, like we did above, which means that du is a single cosine of x dx, or we'll be wanting for our u to be cosine x, which means our du is negative sine of x dx. So if that's kind of the driving force behind what we're wanting to see out of this, it seems to me a logical thing to say that if you have an odd number of, let's say, sines, like this one we have 3 sines multiplied together, and an even number of cosines, what we're going to want to do is to borrow one of those sines. So split sine cubed into sine squared times sine to the first. And I'm going to write that other sine of x at the end. So I haven't changed the integral, I've just changed the way it looks. It's still equivalent to what's right there. Then this part back here will be our du, or part of our du at least. So what that means is that we're using the second situation where u is cosine x. So the sine squared here needs to be written in terms of cosine of x. And the only way to do that I can think of that will work is to use the Pythagorean identity. Sine squared x is replaceable with 1 minus cosine squared x times cosine to the 4th of x times sine of x dx. Okay, so again, we're using this one, and that means that we're missing a negative 1. So I'm going to multiply inside by negative 1 so that all of this is my du. The only way I can do that is if I multiply outside by a negative 1 at the same time. Okay, so doing that substitution, then this becomes the opposite of 1 minus u squared times u to the 4th times du. And of course that has simplified this considerably. We'll want to distribute the u to the 4th through that binomial and integrate the result, which looks like a polynomial. And this is now easy. Powers of u should be extremely easy to integrate. So the antiderivative of u to the 4th is 1/5 u to the 5th. And the antiderivative of u to the 6th is 1/7 u to the 7th. Don't forget your constant of integration, plus c. Now I'm going to do two things in this step. I'm going to distribute that negative, and I'm going to go back to the original variable. So in this problem, our u was cosine of x. So this will be negative 1/5 cosine to the 5th of x, and then distributing the negative, that will become plus 1/7 cosine to the 7th of x plus c. And so that is, in a nutshell, what we're going to be doing with these. So let's look at another example. Again, what I'm trying to do here is to slide you in with examples and to see just why those rules that you're going to see in a minute work so well. It's my intention to make sure that you really understand the thinking process so that this becomes something that you can do. Oh, I started to say, well, the original integral, I forgot to write it down. Well, it's almost this. I think you have it on your sheet. Let me just write it over here. I unfortunately skipped writing the original problem down. There we go. Now, in this particular case, we really don't have much of a choice because of the cube root of something. That something really needs to be our u. So our hands are kind of tied here in that we need to go with u being sine of x, which means du will be cosine of x dx. Okay, so one of the things I would do immediately is what I did over here is I'd rewrite the cube root of sine of x in the denominator as sine of x to the negative 1/3. Then, having made the decision to let u be sine of x, this is fine as is. And what I'm going to need to do is make sure that I have my du, which involves one single cosine of x. So I'm going to borrow one from the 5 of them there and write it separate so that it's extremely clear that I have my du. I have cosine x dx. That's what my du will be. So now doing the substitution, this becomes u to the negative 1/3. Oops, I got ahead of myself, didn't I? Let me back up. Sorry. I was skipping a step, and I really don't want to do that with you at this stage. I don't want to skip too much. So what I said was correct. I just was ahead of myself a bit. Okay, so cosine to the 4th, we need to get rid of that cosine to the 4th and rewrite it in terms of sine. So one thing you can do with even powers is you can rewrite that as cosine squared raised to some power. And remember, powers on powers you multiply. So what would you multiply by that 2 to get 4? Well, the answer, of course, is 2. And the reason you want to rewrite that as cosine squared is because that's replaceable with, according to the Pythagorean identity that we mentioned above, that cosine squared that's inside the parentheses is the same thing as 1 minus sine squared of x. And don't forget that square on there. And so now it's all, except for our du, is all in terms of sine of x, which means we're ready to do the substitution. And this is, I was kind of skipping that step I just wrote. Unfortunately, I almost skipped it. But I don't think I need to do that because that might confuse you. Okay, so every u becomes, or I'm sorry, every sine of x becomes a u, and cosine x dx is our du. So at this stage, probably the best thing to do would be to simplify the integrand, first by doing the squaring. And then do distribution. So we need to distribute u to the negative 1/3 through that trinomial. So u to the negative 1/3 times 1 is u to the negative 1/3 minus 2 times u to the 6/3 plus negative 1/3 is 5/3 plus u to the 11/3 du. Then we have a polynomial made up of a bunch of powers of u, which we will find the antiderivative for by adding 1 to each power and dividing by that new power. So u to the negative 1/3, negative 1/3 plus 1 is 2/3, divided by the new power 2/3 is the same thing as multiplying by 3/2, minus 2 times u to the 8/3, divided by 8/3, which is the same thing as multiplying by 3/8, plus u to the 14/3, divided by 14/3, aka times 3/14, plus c, the constant of integration. Next, we'll go back to our original variable by substituting sine of x in for each u, and we will obtain the following. Was sine of x, so 3/2 sine of x to the 3/2, oops, sorry, 2/3. Almost can't read my own handwriting sometimes. Sorry about that. Minus 3/4 sine of x to the 8/3 plus 3/14 sine of x to the 14/3 plus c. All right, and then let's do another one, another example. This time we're going to integrate cosine to the 4th x dx. And although I'm tempted to think, well, let's let u equal cosine of x, du would involve sine of x, which we don't have. So we're not going to be able to create one out of thin air. And so this is the type of problem where we're going to use that other identity, the power reducing one. So the first thing we're going to need to do is to rewrite this as cosine squared, kind of like the other problem we did, raised to some power. And of course, squaring cosine squared gives us cosine to the 4th. But this time, instead of replacing with 1 minus sine squared, which won't do us any good in this problem because we still wouldn't have a du, what we're going to use instead is the identity the other identity I mentioned, the power reducing one, and cosine squared is 1 plus cosine of double whatever the angle is above. So 2x divided by 2, quantity squared dx. All right, so then doing the squaring, we're going to get 1 plus 2 cosine of 2x plus cosine squared of 2x all over 2 squared, which is 4, dx. All right, well, the first two parts, well, first of all, let me say I'm going to pull that 4 in the denominator out, so 1/4 in front of this. And the first two parts of this, the 1 plus 2 cosine of 2x, that part of it is going to be easy. So I'm going to kind of separate that off from the rest of it. Don't forget that the other part would also have the 1/4. Because this is another problem, I'd be tempted to use u as cosine of 2x, but I won't have my du, which will involve sine of 2x. So I'm going to have to use that identity again. So whenever you have an even power of cosine or sine and no of the other function to be your du, you're going to have to use this, perhaps repeatedly, the identity for power reducing. Okay, so anyway, working on the first part of this, the integral of 1 is x plus 2 times, and the integral of cosine of something, cosine of kx, let's say, because we did this earlier, is 1 over k. sine of kx, so 2x. Okay, and over here we'll need to replace cosine squared of 2x with 1 plus cosine of double the angle above, so 4x now, over 2 dx. So we have 1/4 x plus 1/4 sine of 2x, because of course 2 times 1/2 is 1, and then we distribute the 1/4. Then over here I'm going to pull that 2 out in front. This will be 1/8 of the integral of 1 plus cosine of 4x, which we can integrate. So we have 1/4 x plus 1/4 sine of 2x plus 1/8. The integral of 1 is x, plus the integral of cosine of kx is 1 over k sine of kx plus c. Okay, so distributing that 1/8, we'll have 1/4, which is 2/8 plus 1/8 x is 3/8 x. There is no like term with sine of 2x, so I just copy that down as is. I've already done the 1/8 x. Now I'm distributing the 1/8 to the second thing. That'll be 1 over 32 sine of 4x plus c. Okay, so now if you'll turn to the page in your notes where it has guidelines for evaluating integrals involving powers of sine and cosine, you'll see number 1, if the power of sine is odd and positive, save one sign factor, convert the remaining factors to cosines, then expand and integrate. Just like that, when the power of the cosine is odd and positive, save one of the cosines, and the rest of it will be part of your du. Convert the remaining factors to sines, then expand and integrate. And so our first example or two was like that. And when the powers of both sine and cosine are even and non-negative, you make repeated use of the power reducing formulas, as I did in this last example. So that's a guideline, and it helps you understand when you do what. But basically with sines and cosines, it's based on if you have an odd one of them, like sine cubed, take one of those out to be part of the du, and then that means cosine will be your u. Or if the power of cosine is odd, then take out one of those, and that'll be part of your du, which means u will be sine of x. And otherwise, you have to convert everything into your u, except for the du, which will be, like if it's u is sine of x, then your du will be cosine x dx. That'll be the only cosine in your problem at that point. Okay, so that gets you through the sines and cosines. There's a formula in here called Wallace's Formula, which has sort of limited applicability. If you look at that, if you're integrating from 0 to pi over 2, and it's only that, 0 to pi over 2, a power of cosine, and if you see below that, these also work if it's sine to the nth. But if you have cosine to the nth or sine to the nth of x, where n is odd, bigger than or equal to 3, then you multiply 2/3 times 4/5 times 6/7, etc., until your denominator is n. So if n were 5, you'd do 2/3 times 4/5, and that would be your answer. Okay. Now, if n is even, 2 or bigger, you're going to multiply 1/2 times 3/4 times 5, 6, etc., then times pi over 2, which that pi over 2 is actually part of it. So let's say n is 4. You'll have 1/2 times 3/4 times pi over 2. Okay, so if you have from 0 to pi over 2 a power of cosine or sine, where cosine is raised to an odd or an even power, x dx, then that is a formula to get those. I don't want you to memorize those. If you see the integral in a homework problem that goes 0 to pi over 2 for a power of cosine or sine of x dx, then you might remember and come back and do that this way because it'll be a quick answer. But again, if you don't remember it, you can just do it the long way. It's not going to hurt anything, but it's kind of a neat little trick. All right, so now we're going to work with powers of secant and tangent. And this is a little bit trickier. What we relied on before was that if u is sine of x or cosine of x, its derivative is simply the other function in some form. So for like a u being sine of x, du is cosine of x dx. Or if u is cosine of x, then du is negative sine of x dx. So it involves just simply the other function. And that makes that the easier situation. What we're going to have here is for secant and tangent is a little bit trickier problem. If you have a power of secant times a power of tangent, you're going to want to let u equal either secant of x or tangent of x. So far that looks pretty tame, looks pretty easy, kind of like what we've already been doing. But what is the derivative of secant of x? Well, it's secant x tangent x. The power of, I'm sorry, the secant of x, its derivative is going to involve itself and the other function tangent of x, each one raised to the first power is its derivative. And so you're going to be having to take a du that involves not just one thing, but two. And so that's going to be a little bit more challenging to try to get exactly that form. And our process will be kind of similar, but obviously not exactly the same as with sine and cosine. Now, on the other hand, what's the derivative of tangent of x? Well, that's secant squared x dx, which means we're going to have two secants to be part of our du, not just a single one. So this complicates these problems slightly because of what we need. So let's look at the guidelines first. Let's do that up front this time. If the power of secant is even and positive, so like secant to the fourth of x, what we're going to do is we're going to reserve two of those secants. So basically we're doing this one now, right here. We're going to reserve two of those secants to be part of the du. Then the ones, after we've pulled those two away, we're going to make all remaining secants into something involving tangent. And if you'll recall, the identity here that's going to be fruitful is that for every secant squared x you have, that's the same thing as 1 plus tangent squared. This is one of the Pythagorean identities that you should know from pre-calculus. And that you'll then be able to turn everything in the problem into tangents. pulling two of those secants away and making the rest of them, for each secant squared you have, put in a 1 plus tangent squared in its place. Okay, then the other situation, if the power of tangent is odd and positive, you're going to save one secant and one tangent, so we're now talking about this one. Our u will be secant x, so once we take that one tangent away, we're then going to rewrite the rest of it in terms of secants. So our u is secant of x, so we would write everything in terms of secants. And of course, at that point, we would need to know that tangent squared x is the same thing as secant squared x minus 1, which is just a rearrangement of the one right above it, obviously. Okay, so like I said, kind of like what we did with sines and cosines, just a little bit more complicated. And because of that complication, there are a couple other things that could happen. So look at the next slide. 3, when there are no secant factors, so it's just a power of tangent, and that power of tangent is even and positive, convert a tangent squared factor to a secant squared factor. Okay, that's going to be using what I've wrote there in green. Take one of them, one of the tangent squareds, and do that. And then expand and repeat as many times as you need. Number 4, when the integral is of the form secant to the m of x dx, where m is odd and positive, we'll then use integration by parts. And we'll come back to that later. And then number 5, when the first 4 guidelines don't apply, try converting the whole problem to sines and cosines and see if that helps you figure it out. It's kind of a last-ditch effort. You really don't want to do that as a rule because it makes it a lot more complicated, at least in my view. All right, so let's do a problem. Tangent cubed x divided by the square root of secant of x dx. All right, well, seeing that secant of x under the radical makes me think that I really want to use u equals secant x, so the green one up there above. So I'm going to need to, first of all, I don't like the radical, so I'm going to rewrite this first. Let me do that. Secant of x as a radical, a square root radical, is to the 1/2, and because it's in the denominator, that means it's to the negative 1/2. If we bring it up to the top of the fraction. Okay. Then what we're going to do is we're going to, because we're using the green one, we need a single secant of x and a single tangent of x. So I'm going to take one of the secants away from the secant to the negative 1/2. And if I take one away, that means I'm going to reduce the power by exactly 1. So that would become negative 3/2. And the other secant, let's say, is just over here. Now, if you are curious, that product of secant of x to the negative 3/2 times secant of x to the first should be equal to the power of secant I have above it. Okay, is that true? Negative 3/2 plus 1 is negative 1/2. So I haven't changed its value, I've just changed its look. So I borrowed one of the secants by subtracting from the exponent by 1. Then I also want to borrow one of the tangents. And this is a little bit easier. If I have 3 and I borrow 1, I'm left with 2, because 3 minus 1, of course, is 2. So this will be tangent squared x dx. So I now have my du. That's all of this. And keeping in mind that my u is secant of x, the secant of x to the negative 3/2 is just fine. But I have to get rid of that tangent squared and rewrite that all in terms of secants. So this secant of x to the negative 3/2 is good, as is. And I'm going to rewrite tangent squared as secant squared x minus 1, using that green formula up above. Secant x, tangent x, dx. Okay, now let's rewrite the whole thing in terms of u. So this is u to the negative 3/2 u squared minus 1, and the secant x tangent x dx is underlined above in pink. That's my du. Now simplify that integrand by distribution. So that'll be u to the 1/2 minus u to the negative 3/2 du. And then it's ready to integrate. So adding 1 to that power will make that u to the 3/2 divided by 3/2, same thing as times 2/3, minus u, adding 1 to negative 3/2 is negative 1/2, divided by negative 1/2 is the same thing as times negative 2, plus c. And so our u was secant, so I'm going to now rewrite this answer in terms of secants of x. So this will be 2/3 secant of x to the 3/2. That's a 3, sorry about that. Minus negative, so plus 2 over secant of x to the 1/2, or in other words, square root of secant of x plus c. Okay. One of my rules of thumb is in getting final answers, you really don't want negative exponents. And if you have something that's raised to a fractional power, if the numerator of that fraction is 1, then I'd expect you to write it as like the cube root of whatever. But if that numerator is anything else, leave it alone. So you see this answer, secant of x to the 3/2, that's fine, leave it alone. But because that was u to the negative 1/2, because it's a 1, I want that to be written as a radical, so square root of, and the negative makes it go down to the denominator. Okay, so it looks like I've got a little bit more room. Okay, not much. I think I could do this one. So let's go to example 4, part A. This is the integral of secant squared 5x tangent cubed of 5x dx. Now, don't forget to look for the simple ones. Keep in mind our derivative that we'll use will either be du will be secant x tangent x, as I pointed to here in green, or secant squared. So notice that we have exactly a secant squared there to use. So that means that if we directly make u the tangent of 5x, we already have most of what we need for du, because the derivative of tangent of something is secant squared of that something, then the chain rule kicks in, times the derivative of that something, derivative of 5x is 5, and then dx. Now if you notice, we have almost everything we need there. We already have the secant squared of 5x. We already have the dx. All we're lacking is the 5. So I'm going to multiply inside by 5 and outside by 1/5 so that I have every part of the du that I'm supposed to have. So this one directly becomes a u substitution. This is actually one you could have done prior to this course. In Cal 1, you should have been able to do this. So everything underlined will become du, and the tangent of 5x is cubed, so by substitution that will be u cubed. And then everything underlined absorbs together to become my du. Oops. That did not look good. Try that again. What was... That is so strange. I'm sorry. I have a little bar there that I tried to get rid of, and it just doesn't want to go. Let me see if I can... Nope, that's not going to work. Sorry. I'm a little bit distracted by that bar I'm seeing, and so I'm going to try to get rid of it. What's going on here? Oh, I see what I did. Okay. I can fix this, so just take a second. There we go. I think you could see that too. I'm going to assume you could, and it was bothering me that just kind of a random twitch of my hand that happened. So anyway, back to where we were. That's du. All right, so the antiderivative will be the 1/5 out in front times, we're raising the power by 1, so that'll be u to the 4th over 4. So u to the 4th times 1/4 is what you get there, plus c. And simplifying, that's 1 over 20. And going back to the original variable, that will be tangent to the 4th of 5x plus c. All right. So that completes that one, and this is a good place to stop. So I'll go on to the next recording, and I'll talk to you soon.